Hello students, in last video we have discussed about continuous charge distribution. So considering the case of continuous charge distribution, for different cases how we can calculate the electric field intensity, that we are going to discuss in this particular video. First we'll be starting with the concept of electric field strength due to a uniformly charged rod. So consider a charged rod here. It's having a total charge of Q which is uniformly distributed all over its length. Its total length is L. Now here in different cases we can calculate the electric field intensity. Now first we will calculate on the axial point. That means on the axis on which this particular rod is located at a distance r from one of its end at point P, let's try to calculate electric field intensity. For this, what we will be doing is that we will take a small element of length dx here. It will be having a charge dq. Now from this small element dx, this particular point P is at a distance of x. So this point P is at a distance of r from one end of the rod. Now what we will do is that first initially we will be calculating electrical field intensity due to the charge element dq at point P. By integrating the result, we can calculate the total electric field intensity at point P due to whole rod of length L. So this is a linear charge density condition. So dq by dx will be equal to q by L. From here we can say that dq will be equal to dx. If it goes that side, dq will be q by L into dx. Now electric field intensity at point P due to the charge dq can be given as dE will be is equal to k by k x square into dq. Here k is nothing but proportionality constant, which is 1 by 4 pi epsilon naught. So in the place of dq we will substitute q by L into dx. That means the result we got is dE equal to k by x square into q by L dx. Now what we need to do here is that now we got the result at this particular point P due to the element dq. Now by integrating this result we can find the total electrical field intensity at this point P. Now for integration we need the limits. Means for example, if you take the point P, so this end of the rod is at a distance of r and the other end of the rod is at a distance of r plus L. Now for integration our limits will be from r to r plus L. So we will integrate here. So integration limits will be from r to r plus L, and we will substitute the value of dE we got here. So it will be k by x square into q by L dx. So which will be equal to k, q, L, these are all constants, we will take them out of the integration. So and the limits are r to r plus L 1 by x square dx. You already know that integral 1 by x square will be minus 1 by x. So k cube by L into minus 1 by x into x, and the limits are r to r plus L. Now we will substitute the limits in this place. Now by substituting the results we got as EP will be is equal to k cube by r into r plus L. Again in the place of k, which is constant, we will be substituting the values 1 by 4 pi epsilon naught. So the final result is nothing but 1 by 4 pi epsilon naught q by r into r plus L. That means if there is a rod of length L, if there is a point P which is located at a distance of r from one end of the rod, now the electrical field intensity at that point can be given as 1 by 4 pi epsilon naught q by r into r plus L, or directly in the place of 1 by 4 pi epsilon naught we can use the value k. That means for free space the value of k we already know, that will be 9 into 10 to the power of 9. Now we will see for at an equatorial line, that means there is a point located at the equatorial line at a distance of r from its center. Now we need to find the electrical field intensity at this particular point. Again by the standard procedure we are using for continuous charge distribution, we will take a small element of length dx here. It will be, its charge will be dq. So the electrical field intensity due to this particular point where the charge dq will be dE here. So the distance between here, you can observe that there is a right angle triangle formed. R is the distance from this particular point center O to point P here, and its here x is the distance from center to this element dx here, and for this right angle triangle the hypotenuse will be root of r square plus x square. Now this element we got here dE, its component along this particular axis is nothing but dE cos theta, and its component along x axis is dE sin theta. Here one thing you have to notice is that like this elements we can find any number of elements here. For all the elements, for example, if I take one more element here, again it will be having its y axis component as dE cos theta and x axis component as dE sin theta. Now all the dE sin theta components will get cancelled due to symmetry, and the only left out things will be dE cos theta components. So again for this triangle later we will be using in simplification, we will use sin theta will be opposite by hypotenuse, which is x by root of r square plus x square, and cos theta is adjacent by hypotenuse, again cos theta is r by root of r square plus x square, and tan theta is nothing but opposite by adjacent side, you will be getting it as x by r. Now again this is a case of linear charge density, so dq by dx will be equal to q by L. From that we will find dq equal to q by L dx. So electrical field intensity at point P due to dq can be given as dE equal to 1 by 4 pi epsilon naught dq by distance square here. So from here to here the distance is root of r square plus x square, so that will be squaring here, root of r square plus x square whole square. So dE will be is equal to, in the place of 1 by 4 pi epsilon naught I will substitute k. So dq by here root and square will get cancelled, so we got the result as r square plus x square. Again as we have already discussed, by symmetry all the dE sin theta components will get cancelled, we just need to integrate the dE cos theta component here. So for integration again we need the limits here. So here our reference is the equatorial line. So on the left total length L will be dividing into L by 2, on the left half it will be minus L by 2, and on the right half it will be plus L by 2. So the limits for the integration will be from minus L by 2 to L by 2. So I will substituting the results here. So in the place of dE I will substitute k dq by r square plus x square, and cos theta will be r by root of r square plus x square. So detailed step by step simplification will give the result as EP equal to kqr by L integral minus L by 2 to L by 2 dx by r square plus x square power 3 by 2. So here we will use the concept of integration by simplification by substitution method here. So tan theta is x by r, from that x is nothing but r tan theta. By differentiating this we will be getting dx equal to r secant square theta d theta. So these values will substitute in this particular step. So after detailed simplification, this is a very easy simplification, you can try this. So the result will be r cube secant cube theta. This again will substitute in this particular step. So substituting all the values, we got the result as k cube by L integral minus L by 2 to plus L by 2 cos theta d theta. Again integral cos theta is sin theta. So we got the limits from minus L by 2 to plus L by 2. So this will be k cube by L. In the place of sin theta we already used this relation x by root of r square plus x square, and the limits will be minus L by 2 and L by 2. Now in next step we will substitute the limits. Now by substituting lower limits and upper limits and by detailed step by step simplification, we will get the final result as electrical field intensity at point P on the equatorial line as 2 k q by r into root of L square plus 4 r square. So in the place of k, if you substitute the value of 1 by 4 pi epsilon naught, the result will be q by 4 pi epsilon naught r into 2 by root of L square plus 4 r square. So this is the result for electrical field intensity at a point P, electrical field intensity at a point P situated at the equatorial line. Here small r is the distance between point and the center of the line O here. So in continuation we will discuss about electrical field strength at a general point due to uniformly charged rod. That means earlier we have discussed about two different cases. One case is on the axis of the rod and the other case is that on the equatorial line of the rod. Now in this particular case at a general point, that means somewhere near to the rod, if you consider a point P, So the vertical distance between point P and the rod will be distance r, and which is taking theta 1 with one corner of the rod and theta 2 with the other corner of the rod, and L is the total length of the rod. Now for analyzing situations like that, again as we have already discussed, what we will do here is that we will take a small element dx here. Now because of the element dx, so which is situated at a distance of x from this particular point, so here again a right angle triangle is formed, so its hypotenuse will be root of r square plus x square. Now this particular dx element is having a charge dq here, so because of that there is an electrical field intensity at point P, that is nothing but dE. Again dE will be having two components here, you should be very careful along taking components. So this is the angle theta here, so again this angle will also be theta. So dE vertical component will be dE cos theta, and dE horizontal component will be dE sin theta here. So again from this right angle triangle we will be taking the value of sin theta, cos theta and tan theta. So sin theta will be opposite by hypotenuse, x by root of r square plus x square. Cos theta is adjacent by hypotenuse, you will be getting this result. And tan theta is opposite by adjacent, you will be getting the result as tan theta is x by r. Now here what we will do now is that at point P, earlier this is on the equatorial line. So what happened is that all the horizontal components got cancelled here due to symmetry, but here this is not exactly on the equatorial line, this particular point P. So you have to individually analyze this along x axis and y axis. First of all, let's try to find out what is the electrical field intensity at this point P dE here. So here the electrical field intensity dE is nothing but k into dq by distance whole square. So here distance is nothing but root of r square plus x square. So I'll substitute all the values, k dq by root of r square plus x square whole square. That will give me the result k dq by root and square will get cancelled, and again this is the standard condition of linear charge density. So dq by dx will be q by L, so dq will be q by L dx. So E bar in x direction can be given as dx, which is nothing but dE sin theta, as we have already discussed. So dE sin theta will be, so in the place of dE will be substituting k dq by r square plus x square into sin theta. So this will give the result as in the place of dq substitute q by L dx. So this will give the result as dx is equal to kq sin theta by L into r square plus x square dx. Again here tan theta is x by r, from that x will be r tan theta. So differentiating this we will get dx is nothing but r secant square theta d theta. Now in the place of if you take this particular equation and we will substitute one by one values. So here q by L is nothing but linear charge distribution lambda here, k lambda sin theta by r square plus x square dx. Now in the place of sin theta I will substitute x by root of r square plus x square, k lambda by r square plus x square into x by root of r square plus x square dx. So in continuation here we have r square plus x square, which will be is equal to r square plus in the place of x substitute r tan theta. So this simplification will get the result as r square into secant square theta. Again root of r square plus x square will be root of this result, which will give me the result r secant square theta. So dx will be, I will substitute one by one relations here. So in the place of dE I got the result as k lambda by r square secant square theta. So one by one you can substitute this and try this. So the result you will be getting this as k lambda by r into sin theta d theta. Again here for overall you just need to integrate. So I am taking the limits from minus theta 2 to theta 1. So I am integrating this particular result we got here. So Ex will be equal to integral dx, which will be k lambda by r into integral minus theta 2 theta 1 sin theta d theta. So by substituting the values, upper limits and lower limits, I got the result as Ex is equal to k lambda by r into cos theta 1 minus cos theta 2 minus cos theta 1. So again here in y axis also you can follow the similar process here. So ke y will be ke cos theta, in the place of dE dEy will be dE cos theta. In the place of dE we will get this as k dq by r square plus x square. In the place of cos theta we will get the result as r by root of r square plus x square. So again in the place of dq I am substituting the values here. So the further simplification will give me the result k lambda by r into cos theta d theta. Again in y axis, if you want the total electrical field intensity, I just need to integrate it from minus theta 2 to theta 1. So step by step integration will give you the result Ey is equal to k lambda by r into sin theta 1 plus sin theta 2. So on a conclusion you can say that the electrical field intensity at a particular point means on a general point you can say that in x direction you will get the result as k lambda by r cos theta 2 minus cos theta 1. So again in the place of lambda if you substitute q by r, and for further simplification in the place of k you can substitute 1 by 4 pi epsilon naught. So Ex will be kq by lr into cos theta 2 minus cos theta 1. So similarly in y direction also you got the result Ey as k lambda by r into sin theta 1 plus sin theta 2. In the place of lambda you can substitute q by r, and if you want you can also express the same as in the place of k you can substitute 1 by 4 pi epsilon naught. So these are the different relations we got in terms of a rod. So in the case of a uniformly charged rod in different axes, means on the equatorial line and on the axis on which the rod is placed and on the general point, these are all the conclusions which you need to keep in mind. So I don't expect you to by heart all this process, but the process of obtaining a result is very important. That means there will be many cases where you just need to follow a mathematical procedure for obtaining the results, especially in numericals. So this process of coming to a result is very important, that you need to keep in your mind.